Okay, this next example, 2.2, is actually just a continuation of what we've just been doing. We're still dealing with male and female drivers and the colours of their cars, but we're overcoming the problem we had before. We had an expected frequency of 3.0, which means we couldn't proceed. What this table has done for us, the way we solve that kind of problem, is often to, if we can solve it, the way we'll do it is by putting cells together. It's called pooling cells. So what they've done is they've combined the data for white and yellow cars. So these 3 white cars and these 4 yellow cars for males have been combined into a single figure for 7. And by doing that, when we work out the expected frequencies, we're not going to have any that are less than 5. So having made that change, I now can sensibly do a chi-squared test, and they're asking me to do that. So the first thing I need to do is state my hypotheses, and then I'm going to go on and actually do the calculation. So step 1, always hypotheses. Now these are similar to the ones for correlation. You can use the same word. You can talk about association. Okay, I could use this language as well. I could talk about whether it's independent or not, but you may choose to always stick with the word association because it's equally good for contingency tables as it is for correlation. So I'm going to do that. And remember, H0 is always the boring one, that there's no effect. So H0 is going to be, there is no association. So I say there is no association, but I have to say what it's between. So I have to do this in context. So there is no association between the sex of the driver and the colour of the car. Now for H1, when we did correlation, we had to decide whether this was one or two-tailed, depending on whether we were looking for a particular type of association. But the chi-squared method we're going to use here cannot tell the difference between a positive association or a negative association, because this is non-numerical data. Okay, there's no order of these numbers, so we can't say as the colour of the car increases, the sex of the driver tends to increase, or vice versa. So therefore, our alternative hypothesis for a chi-squared is always kind of like what we'd have used for a two-tailed one for contingencies, is always that there is some association. We never get a grip on whether it's a positive or a negative association, because that usually just doesn't make sense. So my H1 is that there is some association. So we always use the word some, never positive or negative here. And again, I have to say what it's between. So once again, it is going to be between sex of driver and colour of car. So here are my 2 correctly written up hypotheses. Okay, step 2 I'm moving on to now, which is always to calculate the test statistic. And the first stage of that is to work out, from these observed frequencies, to work out the expected frequencies. So I could do the row totals, and I could work out the column totals, and I could use the formula row total times column total over grand total, exactly as we did in the last example. But because I have done those calculations, and all that has happened from the previous example is that these 2 columns of the table have been combined, I'm going to work with the answers I've already got. So I don't need to adjust the first 3 columns, and all I need to do for the last 2 columns, because the numbers of cars have been put together for those columns, I just need to add these numbers together. So I'm just going to transcribe those numbers into the table on the next page for the expected frequencies, and I'm going to add up as I need to for the last couple of columns. So let's get that set up. So for my expected frequencies, for male drivers with black cars, it's still going to be 5.4. This one's still going to be 12.6. I'm still going to have 6.6 and 15.4. Still going to have 5.4 and 12.6. But then for the last 2 columns, for cars that are white and yellow combined, I add these 2 numbers together. So I'm going to get 12.6 here, and adding these 2 together, I'm going to get 29.4. So I've got my expected frequencies. And now I've got to use the formula. So I'm moving on towards this formula here. Now this one actually is given in the formula book. It's actually on page 14. This one is given. the more complicated one that we need when it's a 2 by 2 table, the one that's called Yates's correction. That one's not in the formula book, and the formula for expected frequencies, that one about row total times column total over grand total, this one here, not in the formula book. Okay. Alright, so I need observed frequencies and expected frequencies. I've got those. And I need to do the difference. So it's helpful to put the differences between the observed and the expected in a table of their own. So if I look at my observed together with my expected, so I'm going back to the question as it was originally put. Okay. I might as well have the one there, yes, where white and yellow are combined. So if I look at the observed, and I do observed minus expected, 6 minus 5.4 for the first one is going to be 0.6. Okay, and the second number in that column, the observed was 12, the expected is 12.6. So if I do 12 minus 12.6, I get minus 0.6. And this is not a coincidence, because when we worked out the expected frequencies, we kept this column total. We worked out the column total as 18, and that is the same for the observed as the expected. It has to be, because of the way we work out the expected frequencies. So that means if you've got a column with just 2 entries in it, if one value is more than expected, the other value has to be exactly as much below what was expected. So these two differences are always going to be the same. Now I've put a minus sign on that one because that is what I get when I do the observed minus the expected. But in the formula, I'm going to be squaring these anyway. So when you square a minus, it becomes a plus. So in fact, there isn't a need to record that minus. For the differences here, if we just put in the positive numbers, then we'll be all right. And when we do Yates's correction, in fact, that will be slightly more helpful to us. So I'm going to actually not bother with minus signs anymore. I'm just going to put in the differences. So the next one is observed of, in the next column, 6, and expected of 6.6. So that is a difference of minus 0.6, but I'm just going to record 0.6. So I know what I'm expecting here. I'm expecting the same. Let's check it works. So 16 take away 15.4 is indeed 0.6. Okay, moving onwards, I've got an 11 and I've got a 5.4. So that's actually a difference of, 5.6, 6.6? 11 minus 5.4 is 5.6. Okay, just check that, confirm with the other ones. Difference between 7 and 12.6, yes, that's 5.6 as well. Okay, it is actually worth doing both, so we've got to double check on all the things we've done here. 7 take away 12.6 is actually minus 5.6. And for the last one, 35 take away 29.5 is plus 5.6, and I said I wouldn't bother with that minus. So I've got my differences here, and now I've got to use the formula. So now I've got to do each difference that I've calculated squared, and I divide by the expected frequency. So that's the expected frequency from this table. So I'm going to do 0.6 squared over first one. So for this cell, it's 0.6 squared over 5.4. And for the next cell, it's going to be this one down. Well, let's go across. The next one, 0.6 squared over 6.6 plus 5.6 squared over 5.4 plus 5.6 squared here over the expected, which is 12.6. And then I do the same for the ones on the bottom row. So for this cell, it's 0.6 squared over 12.6. So notice, though, although these two differences were both 0.6, I'm dividing by different numbers because the expected frequencies are different. So although the differences are the same, all of these are going to give different contributions to the actual statistic I'm calculating. And towards the end of this question, we actually have to come back to these and see which ones give the biggest contributions. So I was on to the second row. I've got to do 0.6 squared over 15.4. So that's this term here. And then I've got 5.6 squared over 12.6. Put that right there, and I've got 5.6 squared over 29.4 here. So I've got these terms to add together, and I can just type that calculation into my calculator. So here I've entered the calculation, and you need to do that really carefully. There are big marks getting the right answer here. It's the kind of thing that if you've got time, you need to do it twice and make sure you do get the right answer. So pressing equals, I get my answer. We'll have it as a decimal. So 12.025, 5 significant figures should be enough. So we are going to get as our answer to that, where are we? 12.025. Okay, and that is our test statistic. Okay, step 3, finding a critical value. So we now have to work out the degrees of freedom. There's another formula, and again, it's not in the formula book. The degrees of freedom for a contingency table are the number of rows, -1, times the number of columns, -1. So in this particular case, I've got 2 rows and 4 columns. So it's 2 minus 1, which is 1, times 4 minus 1, which is 3. So 1 less than how many rows there were, times 1 less than how many columns there are, which gives us 3 degrees of freedom. And the symbol used by the table is this symbol. We pronounce it nu, and that equals 3. So in my critical values tables, that's in the formula book. Let's find that. Here we go. We've got percentage points of the chi-squared distribution. Now with this table, we never use this side of the table. Remember, we only are ever interested in high values of the statistics, so at this end. So therefore, if I take my significance level, so going back to the question, the significance level I'm required to use here is 2.5%. So that needs to mean we need to be in the 2.5% at the top tail of the distribution. So the p-value I need is 1 minus that. So for a 2.5% significance level, I need to consider 1 minus 0.025, which is 0.975. So this is my 2.5% significance column, and we said we needed 3 degrees of freedom. So we go down in this column to 3, and the value we need there is this one here, 9.348. So we'll record that. So at 2.5%, we use P equals 0.975. That was 1 minus the 2.5%, and we get the critical value. So chi-squared critical equals what I said, which was 9.348. So I've got a test statistic, I've got a critical value, so we do the comparison. So my test statistic, 2.025, is compared with 9.348. We never look at the negative value of this. Negative values of chi-squared don't make sense. So it's always just a simple comparison. Is this greater or less? It's greater. And that means, okay, this was the value I had to beat. This is bigger than that value. So therefore, this is significant at the 2.5% level. And therefore, my conclusion is going to be that I am going to be, because it's significant, I'm going to be rejecting H0. But of course, we have to interpret in context. So, because I'm rejecting H0, we say there is no evidence, or insufficient evidence would do, but no evidence. Okay, it's nice to state the significance level again at the 2.5% level of, okay, an association. We don't mention a direction of association. That doesn't make sense to this test. So no evidence at this level of an association between, and we have to put it into the context. So driver, sex, and car color. And we're done for the significance test itself. Okay, but there are a couple more things to think about on this question. We need to comment on the 2 most notable differences between the expected and actual data. Now, if we look in the actual raw differences, okay, I had 4 values the same, but the ones that contribute most to the test statistic, these ones with 0.6 squared are not going to make, these are going to be fairly small values. I could actually work out all of these 8 separate numbers, but I can spot which are going to be the 2 biggest values. So this one here, 5.6 squared over 5.4, has got the largest number on top and one of the smallest ones on the bottom. And the next biggest one is going to be this one or this one. In fact, they're the same. So it's going to be a tie for the second one. So the two most notable differences should really say the three most notable differences, and they are, okay, so we talk about males and silver cars, and we have to think, okay, we know this is quite a big difference. We have to go back to the observed and the expected and say whether more or fewer males than expected had silver cars. So the expected number of males with silver cars was 5.6. The actual number was 11. So we say that more, actually we say significantly, because we're commenting on the most notable ones. So significantly more males had silver cars than expected. Okay, significantly more males had silver cars than expected. That's a than, not a then. And the other two, which actually were in this tie, were these two 5.6s, so the ones where I was dividing by 12.6. So that's significantly fewer females than expected had silver cars, and significantly more fewer males than expected had white and yellow cars. But I'm not going to comment on this one. This was not a biggest contribution, because this number, but with the 29.4 on the bottom, is actually quite a lot smaller than these three. So these are the ones I'm commenting on. So I'm going to make two more comments. Okay, I'm going to say significantly fewer females had silver cars than expected. Okay, and significantly fewer males had white or yellow cars than expected. So that's how you comment on the terms that are making a particularly large contribution to your test statistic. Okay. All right, two more things to do. Bit of a marathon, this question. Do the conclusions of this test necessarily apply to the population of all drivers? Well, there was probably a hint earlier on when I was originally given this data, right back in example 2.1. Okay. It says the drivers volunteered to take part in the survey. So what we're looking for here is, was this a random sample of all drivers? If it's not, and it isn't because they're volunteers, then we can't necessarily say the results are valid. So do the conclusions necessarily apply? No, because it was not a random sample, but volunteers. So we prove we've read the question. And explain what a type 1 error would be in the context of this question. Well, it's an error, so I must have done something wrongly. And in a type 1 error, that's when we wrongly reject H0. So if I wrongly reject H0, that's statistical language. We need to do this in context. So that means we would be concluding, well, if we're rejecting H0, we would be concluding there is an association. Okay, it's got to be in context, so I'm afraid I do have to say between driver sex and car colour. Okay, so that's what I'd be concluding, and I have to contrast that with the reality. So we always say when really there is, well, it's got to be an error. So if I'm concluding this and I'm doing so wrongly, it must be really there is no such association. Okay, so make sure that you can interpret what errors would be. That's that one done.